One.
Good afternoon, morning or evening. Okay, we're going to look at a particular experiment today, a Millikans oil drop experiment in electric fields. I was looking back and I forgot to do this particular one before I did the hand-in, but that's okay. We'll still look at Millikans oil drop experiment, and kind of basically what he did was figure out what the charge on an electron was. Okay. So this will be day 8 for us. So let's pop open our, so we're going to do some drawings here, and we're going to talk about electric theory and what he did to come up with the elementary electric charge of an electron. Okay, so that's what we'll do today. So it should take us about, I know maybe we'll do an example calculation problem with Millikans oil drop experiment as well. As soon as we get our board open here. Okay, some schools may even have this stuff around, depending on what kind of a lab you have. Okay, so what we're going to look at today is, this is day 8. Oops, I don't need that. We're going to look at Millikans, and I better spell that right. Oil drop experiment. And this is still in electric fields. I know we had the electric field hand in here the other day, but we should go over this as a cornerstone experiment in finding electric charge, so we should talk about it. So what we're going to do with Millikans oil drop experiment is we're going to outline it. And then look at a sample calculation that he might have done. Okay, so that's what we're going to basically look at. So first thing I'm going to do is I'm going to draw his setup that he had. So basically, Millikan back in like 1909, 1908, somewhere in there, I think 1909 if I remember. Let me look in my little notes here. 1909, he came up with a way. He thought that electric charge must have a distinct charge to it. Okay, a defined charge in discrete amounts. Okay, like you can have 2 coulombs of charge, but how many discrete charges would there be on them? So he wanted to find this discrete charge. So what he ended up doing was he basically used an electric field to suspend droplets in the middle, oil droplets in the middle of air by having 2 charged plates. And then he used the force of gravity on the drop and the electric field charge to calculate what this discrete charge would have been. So let's draw what he had in his experiment. So he would basically have a chamber. So it looks something like this. Now, I'm not the best drawer, but we'll give her a try. Okay, so let's use thin lines. Okay, so he had a chamber. So quite like this. Okay, and then in this chamber, he had two parallel plates. So I'll label everything up. So he had a plate here. Then he had a plate here. Okay, and then he had a microscope or uh, some kind of observing device looking between his plates. Okay, and what he did is he kind of had an atomizer, okay, something that makes things in a spray mister, with oil in it. Okay, so he sprayed in droplets of oil. Okay. And what he would do is he would have a hole in the top plate, okay, and he would take these plates are charged plates, so these are charged. Okay, so on the charge plate, this would be the positively charged plate that he did. And then he could adjust the voltage between the plates. Oops, this would be negative, pardon me. Okay, so he'd spray these in, and then he had a battery here or a power supply. Okay, and he could adjust this. Okay, so what he did was he'd spray these in, okay, these droplets of oil. Then he would he had a way to adjust his voltage between the charge plates, and these things would kind of float down, and they'd reach terminal velocity, and they'd be falling down, and he would adjust the voltage between the plates until he suspended a droplet of oil. Now, why would this drop be suspended? It would be a negatively charged drop. Okay. And then he suspended this drop in the middle here. And you're like, well, how did this get charged? Well, these droplets, as they come out of this atomizer tube, they get charged by friction. So some would be positive and some would be negative. And if they would fall down in here, and he had a little hole, and then he'd get one in there or a bunch in there, and he would suspend. He'd adjust it, and the ones that are floating there, he could see, and you could see the size of them, and you're like, okay, well, that's kind of neat. So it was floating there. Now, that electric force is what's suspending it against gravity. So then Millikan had to find out how much it weighed. So he would use, okay, after he would suspend the drop, okay, so a negative drop would suspend. Okay, due to the fact of the electric force equaling between the plates equaling the gravitational force. Force of gravity on the drop equaled the electric force Okay. So then he would have to know, well, he could measure that electric force, but he would have to know the mass of this drop. So he did the way that he found, he needed two measurements. He needed to find out the electric field, which we know is just, as we've worked on a couple days back, it's just the change in the voltage divided by the distance between the plates equals the electric field force, newtons per coulomb. Okay, and the gravitational force would just be mg. Okay, so the negative drop becomes suspended because of that. Okay, he measured the mass of drops.
Do you have the bad keys?
I do, in my pocket.
Take the Cameron Neville buses.
Yeah. Good thing I went home and got them at noon.
Nice.
And no worries. Okay, so he basically, okay, he had that drop suspended there. Okay, and the negative drop would become suspended because of the force of gravity. So he measured the mass of the drops by a complex equation, which is beyond us here. When he watched them fall without the electric field on. So he'd spray them in there and then they'd all kind of float down to the bottom, and he could calculate the mass of it based on the gravitational field of the earth and all that kind of stuff, and how long, and the air resistance. And it wasn't just like where we did it where we ignored friction. He had a equation that included what the friction on the air was and all this other kind of stuff. So he measured the mass of the drop by a complex equation as the drop fell. Okay. Okay, so he knew mg, he equaled it to the electric force, and then he was able to calculate the charge. Okay, using this, he calculated the charge on the drop with Fg, force of gravity, equaling Fe, the electric force. He calculated the charge on the drop. Okay, and then how many electron charges was it? Well, he didn't know, but he did this a lot of times, and he was able to isolate that the common integer or multiple. Okay, so then he did this many times. Okay, so he found a common multiple of charge. So it's a math exercise. Okay, did this until he found the common multiple of charge, which was the elementary charge. And that elementary charge we call charge on an electron, E negative, was 1.6 times 10 to the negative 19 coulombs. Okay, and that's what he did. So he kind of sprayed in some drops, had these charge plates, had an adjustable power, so he could change the voltage, got a drop to suspend. He would calculate that, he would watch that drop fall, and he would calculate, what its mass was, and then he would get it suspended. This would have to be a negatively charged drop. So he'd watch it fall. He wouldn't watch it fall all the way to the bottom, obviously, right? He would watch, there was a hole in the plate, and he'd watch it as one came through. He'd watch it fall, and then he'd use that complex equation, and then he'd stop it from falling. He'd adjust it so that he would suspend it so it didn't move up or down anymore. And then that was what he would do. Okay? And that's how he figured out, and he did that in 1909. Okay? And he figured out the elementary charge was 1.6 times 10 to the negative 19 coulombs to two significant figures. Nowadays, they've used very good equipment, and they've went down, according to, let's see what it says in my background here, they've gone down to like 1.60217653 times 10 to the negative 19, but we don't have to go any farther than 1.6 in our case. And we used to use this when we talked about current electricity, but that's not part of the course anymore. Okay, so let's do an example. Let's see what we got for time here. Oh, good, 15 minutes, perfect. Okay, so let's do an example of how he did the calculation from a Millikans experiment type idea. So let's do that on the next page. Okay, so let's say that we have this situation. Let's say in a Millikan drop experiment, see if I can spell this name. And so in a Millikan drop experiment, a particular oil drop, let's see here, I got it. Okay. Weighs, okay, we're not going to go grams. Remember, weight is going to be in newtons. It's going to be a force. 2.4 times 10 to the negative 14 newtons. So he's already converted the grams into newtons by multiplying by Earth's magnetic or gravitational field of 9.8. Okay, and we'll talk about that when we talk about gravitational fields. So let's get that there. I guess we should keep it there. Okay, and we'll turn that off. Okay, so 2.4 times 10 to the negative 4 newtons. Okay, that's its weight. The parallel plates are separated by a distance of 1.2 centimeters. I'm just getting one out of a book here. 1.2 centimeters. Okay, and when the potential difference is 450 volts, the drop is suspended. We'll say voltage. Period. Find. So what can we find here? First thing we can find is what is the net charge on the oil drop? I guess we should put that as A, sorry. We'll do 2. Okay, so what is that charge? And it's going to have to be a multiple of that. And then how many electrons, how many excess electrons are on the drop? If the top plate is positive. It has to be, right?
received the direction today that dismissal time, all of the average bus students that go on Hollywood bus, all of the students that go beyond Cameron, Chanel students are.
Okay, so that's what we're going to figure out here. So let's, the first thing I always do is I just kind of draw what's happening here. So let's draw, we don't have to draw the chamber, we'll just draw the two plates and the drop. So here we have our positive plate. Okay, we have, well, let's give ourselves some more space to draw it here. Our negative plate on the bottom. So we have this drop of oil suspended where we have a force pulling it up towards there. That's the force on the electric force. We'll call it Fe. And we know that that's just the charge times the electrical field strength, according to our electrical field charge. Okay, and then we have the force of gravity pulling it down, that's equal. Okay, and the force of gravity is going to be mg for us. Okay, mg, mass times gravitational constant. But it's going to basically be, this is already mg, right? It's so many newtons. Okay, so we've got that. We know that the change in voltage is 450. We know that the distance between the plates is 1.2 centimeters, which we should change to meters. Okay, and that's going to help us out there. We also know that we have a weight, or the force of gravity on the drop is equal to 2.4 times 10 to the negative 14 newtons. Okay. Now, what we want to find is we want to find out what is the charge on the drop. Okay, and then after that, we want to find out how many electrons, which we could easily do by just dividing the total charge by the elementary charge that he gave us. Okay, so let's figure out how are we going to do this one. Okay, so basically we have to equate this gravitational force to this electric force. So both of these Fg and Fe are equal by theory. Okay, so if we know that Fe is equal to this equation and Fg is given right there, we can say then, therefore, that 2.4 times 10 to the negative 14 newtons is going to equal Q times the electrical field strength. Okay, now we also know that the electrical field strength has a formula for it as well. Okay, so we know that the electrical field we know from before, a couple days back, I guess, that electrical field strength is going to be equal to, if we look back, it's equal to a change in the voltage over the distance. Or if you look back in one of our lessons that I did that, we wrote it out as E voltage. We wrote it out like this: voltage equals E times V, or sorry, E times D. I was going to put change in voltage down twice there for whatever reason, right? So I'm just rearranging it. Okay, we wrote it like that. Okay, I'm just going to pause here while we have people run through their lockers here, and then I'll unpause it and finish this off after that. Okay, just resuming there. Sorry about that. So just looking back, just in case you forgot, from a few days ago, how much work is done. It's electric field size times the distance between the two will give you your voltage. So we're just rearranging it but by dividing both sides by D. So that's where we get this equation. So if we plug this into here, okay, so if we plug in for E, we get, I guess we should have left that as a variable to start. We plug this in for E, we get F, G, or Fe, or force, we'll just say force for now, doesn't matter which one we put, is equal to Q times change in voltage over D. Okay, so this is our full equation that we can use now. So now if we plug in our numbers, 2.4 times 10 to the negative 14 newtons equals Q times 450 volts divided all by the distance of 1.2 centimeters. In meters would be 0.012. Okay, so then if we take our calculator, okay, well, simplify it. 2.4 times 10 to the negative 14 equals Q. And we'll take a calculator out here if I can find it. There it is. Okay, so in our calculator, we go 450 divided by 0.012. That gives us 37,500. Okay, and that's voltmeters, right? Okay, and then if we work this out, we divide both sides by that number. So we take 2.4 exponent or scientific notation negative 14 divided by 37,500. So we get 6.4 times 10 to the negative 19 for our charge. Okay, and that's going to be coulombs. So that's A. Okay, so then if we had that, okay, how many electrons would it be? Well, if we know that for B, we can say that a charge is equal to N times E. Okay, so this is our charge. And this is our number of electrons. Okay, or missing electrons if it's positive. Because if it's positive, it's extra electrons if it's negative, right? And it's missing electrons if it's positive. And this is our elementary charge. Okay, which Millikans actually did figure out. So in our case, we had 6.4 times 10 to the negative 19 coulombs equals N times 1.6 times 10 to the negative 19 coulombs. So N looks like it's going to be what, 6.4 divided by 1.6? 4. So you have 4 electrons. Sorry, guys. So that's a typical type of question. Now, what he did is he didn't know what the elementary charge was. So he just kind of looked for a lowest common multiple between a whole bunch of results and was able to figure that out. Okay. So that's a Millikan oil drop experiment. So again, just to summarize it, okay, he had a chamber. He suspended 2 plates in the chamber. He had an atomizer that shot droplets of oil above it here. He had a little hole in here. Okay, and then what he did was he looked in, okay, and he calculated how fast it fell, and that because of complex equations with air resistance and all that, he was able to figure out that are beyond us here and stuff we don't need to know. He figured out how much mass or weight, in this case, in newtons, that drop was. And then he adjusted the power supply so that the oil droplet would be suspended in midair. Then he would take that result, did a calculation similar to what we did, to calculate what the charge was. He found the charge. Okay, now he didn't know what the charge on an electron was, so he had a charge. Then he just looked at a whole bunch of variety of samples and looked for a common multiple, lowest common multiple kind of exercise in math. And that lowest common multiple, whole number, gave us the elementary charge. In this case, we had 4 electrons. You would have had other ones, with different masses and stuff, and they would work out to a discrete. They would either be 1.6 times 10 to the negative 19 coulombs bigger or less if they had 5 or 6 or 7 or 8 or hundreds. Okay, and that's how he kind of did that Millikan oil drop experiment. Okay, so I forgot to mention that when we were doing electric fields, so I thought I'd put it in there. Looking through my background notes here as well, I think I've pretty much got everything else in there. We could have maybe talked a little bit about capacitance. Okay, capacitance is also in there as well. So maybe we should define a little bit about capacitance. What do we got here? Yes, we got just enough time to kind of say what capacitance is. So along with Millikan's oil drop experiment, I should have mentioned for you guys what capacitance is, or capacitors. And what these are basically, a capacitor is they're like little, you can probably see them on electric boards, they're like little tubes and stuff, and what they do is they store charge. Capacitors store electric charge. So when you're talking about capacitance, it's basically you're just basically making one of those electric fields. And what they do in a capacitor is they usually wrap it. They don't usually have it flat, but you could have parallel capacitors, and they'll store electric charge. Okay, so if you're thinking about what capacitance is, it's the ratio of charge that you can store to the voltage that you need to store them. Okay, and I think that it's pretty straight line. Okay, so capacitors store electric charge. The formula to calculate the capacitance of a capacitor is pretty easy. Okay, and I'll switch over to my marker here. Okay, C equals Q over V, which this is our charge. This is our voltage or potential difference. And C is our capacitance. Okay, so call this capacitance. Okay, and capacitance, okay, charges in coulombs, voltage in volts. And capacitance, I think they have a unit for it. I think it's called a Faraday. Yes, this is measured in Faradays. Named after Michael Faraday. Okay, and that's capital F. So that means 1 Faraday equals 1 coulomb per volt. Okay, so basically, capacitors, you're just basically setting up an electric field idea of a positive and a negative charge to store that charge in. Okay, so let's do a quick example of that, and then we'll have to stop there because I'm going to run too long here. Okay, so let's say a sphere is connected. Oh, let's see. No, that one's too hard. Okay, let me just pause and I'll find a simpler one than that one for you guys. Sorry about that. Okay, so a capacitor. Let's do a quick one here. A capacitor has a 27 micro farad rating when 45 volts of potential difference is run across it. Find the charge stored. Charge stored in the capacitor. Okay, so these are the typical or more typical to what we would do. Sorry, guys. So microfarad, we have to remember that the capacitance, okay, it's going to be 27 times 10 to the negative 6 farads. Okay, we know that the voltage is 45 volts. And we know that the charge is unknown. Okay, so if we rearrange our capacitance ratio formula to get charge is just equal to the capacitance of the capacitor times the voltage across it. If we multiply both of those out, so the charge of this is just going to be the capacitance, 27 times 10 to the negative 6 farads times 45. Okay, volts, pardon me. Okay, so if we take our calculator out, 27 exponent negative 6 times, our scientific notation, pardon me, negative 6 times 45 equals 1.2, if we round it off to two significant figures, 1.2 times 10 to the negative 3 coulombs. Okay. So I did forget about, I apologized for you guys. I did forget there before I put up the before I put up the hand-in assignment, I did forget about Millikans oil drop experiment and capacitance. And luckily I looked back in my notes and we just did a little run through. Will you end up having something on capacitance on your next hand-in or quiz? Probably not on your next hand-in because it's going to be about gravitational fields. But it might show up on the quiz, a simple question like this. Okay, so we'll stop there. That's a good 41 minutes in, so that's far enough for today. And we'll get into the gravitational stuff next day.